Welcome to Spring LIB.
As we know, sound waves are divided into three categories that cover different frequency ranges. Audible wave lie within the range of sensitivity of human ear that can generated in a variety of ways, such as by musical instruments, human voices, or loudspeakers. Second is infrasonic waves have frequencies below the audible range. Elephants can use infrasonic waves to communicate with one another, even when separated by many kilometers. Third is ultrasonic waves have frequencies above the audible range. You may have used a silent whistle to retrieve your dog. Dogs easily have the ultrasonic sound this whistle emits, although human can't detect it at all. Ultrasonic waves are also used in medical imaging. As we know, the harmonic position function is given by S of x of t is equal to S max times cos kx minus omega t, where S max is equal to A is the amplitude of the maximum position of the element relative to equilibrium. K is equal to 2 pi by lambda is the wave number, and omega is 2 pi by t is equal to 2 pi nu is the angular frequency. Now, as we know, the variation in the gas pressure delta P measured from the equilibrium value is also periodic with the same wave number and angular frequency as for the displacement, which is given by delta P is equal to delta P max sine kx minus omega t, where delta P max is equal to B S max, K is equal to rho v omega S max is the pressure amplitude or the maximum change in pressure from the equilibrium value. As we know that the power is the rate at which the piston is doing work on the element at any instant of time is given by power is equal to F times V of x vector. Also, we can express the power as delta pi times ds over dt I is equal to rho v omega square a s square max sine square kx minus omega t. As we know, the intensity of wave I is defined as the power per unit area, which is the energy transported by the wave transfer through a unit area perpendicular to the direction of the travel of the wave, where I0 is equal to 1 into 10 to power minus 12 watt per meter square is the reference intensity. Now, the intensity I is average power divided by A. So let's put the equations over here. So we can write 1 half rho omega square S square max times V. That will be equivalent to delta P max square upon 2 rho V. that is my intensity I. Also, we know that for the spherical wave, the intensity is given by I is equal to average power divided by 4 pi r square, because the waves are spherical over here. At no, we should define the sound level concept. The sound level beta is convenient to use a logarithmic scale. So beta is equal to 10 log I over I0. As we know, the sound of a vehicle's horn changes as the vehicle moves past you. The frequency of the sound you hear as the vehicle approaches you is higher than the frequency you hear as it moves away from you. This is one example of the Doppler effect. According to Doppler shift, for the observer moving towards source can be defined in the form of equation as V dash is equal to V plus V0 over V minus Vs times V, where V0 is the observer speed and Vs is the source speed. Also, we know that the observed wavelength lambda dash is given by lambda dash is equal to lambda minus delta lambda is equal to lambda minus, because delta lambda is Vs upon V. As we know, for shock wave, the match angle theta is given by sine of theta is equal to V over Vs. Now, the solution of part A, as the problem mentioned, the tsunami speed is given by V is equal to square root of GD. So the water speed is directly proportional to the ocean's depth. If the ocean's depth increases, then the water speed increases. As we know, the changing in the total energy is constant according to conservation law of energy. Also, periodic time is constant through one wave. Now, for the solution of B, we can say that as we know, the water's wave amplitude is inversely proportional to the square root of speed of water, that is, A is proportional to 1 over square root of V. As we mentioned in section A, the water's wave speed is directly proportional to the ocean's depth, so the wave approaches shore constantly. Consequently, the ocean's depth decreases. Consequently, the water speed is decreases, so the amplitude of the water wave increases. Now, for the solution of part C, as we mentioned before in the concept session, the water's wave amplitude is inversely proportional to the square root of the speed of the water, which is written here. So, we are going to solve for the first case. So, in that case, I can write A1 is equal to 1 upon square root of V1. And for the second case, A2 is 1 over square root of V2. So the two equations are equal. So I can write A1 square V1 is equal to A2 square V2 is equal to A2 square, because we have V2 is equal to square root of g d2. Now rearranging and solve for the amplitude A2. So the A2 will be equivalent to square root of A1 square V1 divided by square root of GD2. Now let's put all the values here. So in the square root of 1.8 into 200 upon in the square root 9.8 into 9. So the answer will be 8.307 meter. Moving further, as we know, the amplitude of the wave is maximum at the shore. Also, the water speed in the case of tsunami is less than the water speed in the normal case.